Good evening, everyone. So today we are going to see a very interesting application of Polya's enumeration formula. So using Polya's formula, we are going to compute the number of non-isomorphic graphs. So let's quickly revise what it means by non-isomorphic graph. So when we talk of a graph, then graph looks something like this. So there are some vertices like 1, 2, 3, 4, any number of the vertices, and there can be edges between them. It is not like every pair there are edges. Like this is also a graph, I can add more edge. This is also a graph, I can keep one more edge. This is also a graph. I can add 2 3 edges between the same pair of the vertex. This is also a graph. I can add an edge with both the endpoints as the same vertex. So all of these are said to be graphs. Yes. Now, how do we say the two graphs are isomorphic or non-isomorphic? So mainly isomorphic means that first, whenever we talk of the isomorphism, they have same vertices. If for example one has 4 vertex and the other one has 5 vertex, then there is no point in saying isomorphism. Of course they are non-isomorphic. If they have different number of the edges, again they are not isomorphic. The problem comes when they have same number of the vertices and same number of the edges. For example, G1 and G2. 5 vertices, 5 vertices, 6 edges, 6 edges. Now, are they isomorphic? Are they not isomorphic? See, there are many ways of drawing a graph. Therefore, it is not possible to check isomorphism by just looking at it. We have to see, does everyone exhibit the same property. So for example, degree means the number of the edges incidenting to each vertex. So u1 3 vertices are incidenting, u2 2, then 3, then 2, then 2. Here also 3 3 2 2 2. If degree didn't match, so 3 3 2 2 2, here also 3 3 2 2 2. If it didn't match, we can directly say they are not isomorphic. Now degree is also matching. Then what else? Here degree 3 vertex and degree 3 vertex are not adjacent. There is no edge between them. Here also degree 3, no edge between them. Degree 2, degree 2, degree 2, no edge between them. Degree 2, degree 2, degree 2, no edge between them. So you can see that both the graphs having the same property. And now just is a small graph for the verification. You can see that I can draw G1 same as G2. So if I pull back V2, you can see this is V2. Now I am putting it here and making V3, V4, V5 adjacent to V2. Then I will get almost the similar graph. And that's why I can say that G1, G2 are isomorphic. For better understanding, let us consider one more example. Are these two graphs isomorphic? Now 5 vertices, 5 vertices. Let's count the edges. So 1, 2, 3, 4, 5, 6, 7, 8. Here also 1, 2, 3, 4, 5, 6, 7, 8. Yes. Now let's count the degree. This is 3, this is 2, this is 3, this is 4, this is 4. I count it 4 because 1 edge, 2 edge, then 3 edge and 4 edge. So 4 4 3 3 2. Here 3 3 4 2 and 4 4 4 3 3 2. Yes. Now let's see a property. This is degree 4, this is degree 4, and there is an edge between degree 4, degree 4. This is degree 4, this is degree 4, but there is no edge between degree 4, degree 4. That's why they are not isomorphic. Yes. So now the problem is to count the number of non-isomorphic graphs. Clear? And also when we say non-isomorphic graphs, we are considering few things. One is unlabeled, because labeled and unlabeled, it matters a lot. For example, these two graphs are there, they are isomorphic, but if I give the labeling like 1 2 3 4 and here I give 1 3 2 4, then you can say 1 2 are adjacent here, which are degree 3 degree 3, or for example 2 4 are adjacent here but 2 4 is not adjacent here. But if you say unlabeled, then these two are clearly isomorphic. So I consider the unlabeled. Then I consider simple graph. Simple graph means that between two vertices there should be only one edge, because there can be more than one edge also, like this is also allowed, two vertices 1 and 2 and 4 edges between it, but I am considering only one edge. And no loops. What is a loop? Loop means there is a vertex and there is an edge starting and ending here. Yes, if I say this is 1, this is 2 and there is an edge, this is loop. So multiple edges, loops I am not considering, and labeling I am not considering. Now I have to find number of non-isomorphic graphs on 4 vertices. You can try to find it by yourself. The idea here is that I can start with minimum edges, because 4 vertices are fixed. So I can start with minimum edges and goes to maximum edges. So if I start, this is my first choice, 0 edges. Then I can introduce one edge, there is only one way. I can introduce two edges. Now for two edges there are two ways. One is you join these two dots, something like this. Yes, or the other is you leave one dot. There is no other way. Yes, now I add one more edge. For one more edge, from 3 I will get this. So this is my fifth one. Okay, from fourth I can get this one. This is my sixth one. And from fourth there is one more choice, like this. This is my seventh one. If from fourth you will, like this is your fourth, and if you do like this, this is already covered as fifth, so I don't consider it. Then eighth one, so from fifth if I go, this is my eighth. From sixth I can do like this, so this is my ninth. From 8th I can do one more, this is my 10th, and from 10th I can add one more edge, this is my 11th. I cannot add more edges now because I need only one edge between a pair of vertex. So minimum edges are 0, maximum are 6. Yes. Now there is no such formula to compute the number of non-isomorphic graphs. Okay. And it's a graph theoretical problem which is not easy to address. Now we are going to address this problem using the concept of Polya's enumeration formula. So to proceed further, first we will consider a symmetric group on vertices. So here this symmetric group S4 means it consider all the symmetries. All the symmetries means 4 vertices are there. So all cycles of length 4, or all combinations, 1 cycle of length 2, 2 cycle of length 1, 1 cycle of length 3, 1 cycle of length 1, all cycles of length 4. Why is it so? Because if you consider any graph, for example, if you consider this graph, yes, for example, you consider fifth one and you say 1 2 3 4 vertices are there. If you interchange any one of them, for example 2 3, you make 3 2 1 4, so the change in terms of the adjacency, here 1 2 is adjacent, here 1 3 is adjacent, but there is no change in terms of the vertices. The graph remains same. If you see in terms of the vertices, then there is no change in the graph if edges are not considered. So that's why what we do is that first we consider the symmetric group S4 on vertices, and from there we will compute a symmetric group on edges. It would be clear once we proceed further. Okay, what has happened? So let's move to this slide and from current slide. So I will start for N4 and compute S4. So for S4 I have to consider all possible combinations. So for example, if I consider 4 cycles of length 1, then the cyclic structure is x1 raised to the power 4 or s1 raised to the power 4. Now if I consider the permutation of this form, then it's look like there are 2 cycles of length 1 and 1 cycle of length 2. Just a minute. So now the other possibility is there are 2 cycles of length 1 and 1 cycle of length 2. And in this case there are total 6 possibilities are there. So something like this, 1 2 1 3 and the other cycles of length 1. Again I am telling you symmetric group of length 4, it means we are considering all possible combinations, because when we are interchanging the vertices, then they matters when we consider the edges, otherwise not. So that's why we have to consider the cyclic structure of edges to count the non-isomorphic graphs. The other possibility is 1 cycle of length 1 and 1 cycle of length 3, and there are total 8 possible combinations. Similarly, 3 combinations for 2 cycles of length 2, and there are 6 possibilities for cycle of length 4. So if I have to write down the cycle index in this form, then this is how it looks like. Now for the edges, I just make a representation that an edge is represented as ij, and ij is same as, so if there is an edge between 1 2, I represent it as 1 2, which is same as 2 1. Okay, and now from here I will consider the cycle index of, which I denoted as ZS4 square, which means for the edges. It would be clear now when I explain it. So for example, in S4 it is S1 raised to the power 4 because 4 vertices are there, but in terms of the edges there can be 6 edges, and therefore the permutation would be S1 raised to the power 6 because 6 edges are there. Now let's say you have permutation 1 2 3 4. Yes, when you interchanging the vertices, on vertice group there is no effect, but on edge group there is a effect. On set of the vertices it remains 1 2 3 4, but set of the edges get changed. How? Let's see. So initially let's say you have 1 2 3 4. Now you interchange, 1 2 remains as it is and 4 comes here, 3 comes here. Yes, now observe what is the changes. So 1 2 edge remains as it is, but 2 3 and 2 4 get interchanged. This is 2 3 and this is 2 4, and 1 3 and 1 4 get interchanged, and 1 2 remains as it is and 3 4 remains as it is. So that's why you have 2 cycles of length 1 and 2 cycles of length 2. Yes, similarly for all possible combinations you have to see how it behaves. For example, in this case, when there is 1 cycle of length 1 and 1 cycle of length 3, how the edge set get changed. So for S4 it is S1 S3, but for the edge set it becomes S3 cube. You can observe that 1 2 3 4 becomes 1 2 1 4 1 3. For example, this is 1 2 3 4, and you change 2 to 4, sorry, so 1 remains as it is, and 2 reaches to 4, 4 reaches to 3, and 3 reaches to, and you can see how it is behaved. So 2 reaches to 4, then the 4 reaches to 3, and 3 reaches to 2. Yes, so clearly 1 2 becomes 1 4. You can see this is 1 4, then 1 4 get changed to 1 3, and so on. So similarly, if you keep observing this one, I have already given the details, then you will find that the cyclic structure in terms of the edge set would look like this one. Yes, but from here I do not get any information on the number of the graphs, because to use the Polya's enumeration, if you recall in terms of the two coloring, we used to replace xj by bj plus wj, which means how many black and how many white colorings are there. In terms of graph, you can categorize as, is there an edge between a set of vertex? So there is not an edge between set of vertex. For example, 1 2, this is 1 2, there is no edge between it, and 1 2, there is an edge between it. Yes, so this classification clearly gives non-isomorphic graph. So if I associate a weight and if I think in terms of ordinary generating function, so it means the generating function would be x raised to the power 0 plus x raised to the power 1 if there is a cycle of length 1. It means there is an edge or there does not an edge. If I write 1 2, so corresponding to 1 2, if the generating function is 1 plus x, it means either 1 2 exists or 1 2 does not exist. But if there is a cycle of length 2, for example 1 2 and 2 3, it means these two edges exist or does not exist. It means the corresponding generating function is 1 plus x square, because when I form this cycle, then I have to say, like in this case, either 2 4 1 3 exists or 2 4 1 3 does not exist. Therefore corresponding generating function is 1 plus x square, and here 4 edges are there, therefore corresponding generating function is 1 plus x raised to the power 4. If I do all these replacement here, then you will observe that my required generating function looks like this one. Now this gives a lot of information. X6 means there is one graph with 6 edges. S5, x raised to the power 5 means there are two graphs with, there is only one graph with 5 edges. Then there are two graphs with 4 edges, and so on, and in total if you count them it comes out to be 11. So using Polya's formula we will get that there are 11 graphs, and in those 11 graphs how many graphs are there with how many edges. Okay, so very interesting application of Polya's formula. In the next class we will start a new chapter. Thank you.